All right, here we are, ready to what? Ready to finish off our harrowing descent into the dark yet exciting nether corners of hypothesis testing. Now, at this point, maybe some of us, who knows, perhaps all of us, are starting to notice some parallels to sort of the journey that we took through confidence intervals. So we learned three types of confidence intervals, didn't we? We learned a confidence interval for the mean when the population standard deviation is known. We learned a confidence interval for the mean when the population standard deviation is unknown. We learned a confidence interval for a proportion. Those were the three that we learned. In terms of hypothesis testing, what have we learned? We've learned a hypothesis test for the mean, the population standard deviation known. We use a z, just like in the confidence interval. We learned a population standard deviation for the mean, population standard deviation unknown. We used a t, just like we did for the confidence intervals. And so perhaps not surprisingly, our last stop along the hypothesis testing express is a hypothesis test for proportion. Now, the hypothesis test for proportion is not that different from the hypothesis test we've already learned how to do. There's still 4 steps, for example. Step 1, set up our hypotheses. Step 2, construct a test statistic. Step 3, oh man, I can never remember. What's step 3? Maybe you could remind me. Oh, that's right. Step 3 is calculate our p-value. Thank you. And step 4, perhaps the most important one, make our conclusion. So we have the same 4 steps. Now, a little bit of differences. For example, the first step, well, we're no longer working with the mu. We're no longer working with the population mean. We're instead working with the population proportion. So if you look at how we set up our hypotheses, there's no longer mu's and mu naughts. There's p's and p naughts. No longer population mean and hypothesized population mean. It's now, right, this sort of true population proportion, and this p naught, some value, some number, some hypothesized proportion. But other than just replacing mu's with p's, it's still the same. We still have the sort of 3 cases: less than, greater than, not equal to.
The formula that we use to generate our test statistic, it looks different, and technically it is, but it's conceptually the same formula. Just like before, right, the whole idea of the test hinged on how far is the sample mean from the hypothesized mean. Similarly, the entire test of a proportion hinges on how far the sample proportion is from the hypothesized proportion. That's what's in our numerator. What we have in the denominator can be shown to be the standard deviation of the sample proportion under the null hypothesis. So we're dividing by that standard deviation of p hat, just like we're before. So we're looking at the distance between the sample proportion and the hypothesized proportion in units of standard deviation. So the test statistic still has that same interpretation under certain conditions that we won't really bother getting into. This test statistic follows a normal distribution with a mean of 0 and a standard deviation of 1. Hence, we call it a z-test. Steps 3 and 4 are exactly the same as our large sample hypothesis test for a mean. Once we have our test statistic, we calculate p-values in the exact same way that we did in our large sample test and our z-test, and we draw our conclusions in the exact same way by comparing p-values to significance levels. We can do this in our calculator, not surprisingly, by hitting the Stat button, going over to Tests, and selecting one prop z-test, because it's a z-test, it has a z-test statistic, and it involves just a single proportion. So, let's do 3 examples to get better acquainted with this testing procedure. The first example is a nice sports example. So, the average NBA free throw percentage is 75%. The recently retired Allen Iverson, right? He actually, he had his official retirement at a Sixers game last March, I believe. Although if you're listening to this 5 years from now, I guess it won't be last March. But It's always been said that Allen Iverson, say what you may about him, was a better than average free throw shooter. Some seasons back when he was playing regularly, he made 80% of 225 shots. Let's use that information. Let's make that our sample and use it to test the claim at the .05 significance level. Now, before I go to the next slide, what is our alternative hypothesis going to be? It's thought that AI is better than average. So our alternative hypothesis is going to be that P, right, the probability he makes a free throw shot, that P, his probability, is greater than 0.75. And sure enough, here it is, our null and our alternative hypothesis. And just like before, the null hypothesis is always a statement of equality. In this case, we're saying that P, the probability that he makes a successful free throw, is 75%. Now, like before, we can use our calculator to handle steps 2 and step 3. But to do that, we need to fill in the information into our calculator. So the first line is P naught. That's our hypothesized proportion. The second number, just like in the confidence intervals, is essentially the number of successes, right? In this case, the number of free throws that he made. We were not given that number in this problem. Nonetheless, we could find it. We know that he made 80% of his shots, and we know that he took 225 shots. So all we need to do is figure out what's 80% of 225. To do that mathematically, we just do 0.80 times 225. We can actually do that within the one prop z-test menu. So notice on the X line, I've written in 0.80 times 225. When you hit enter, or when you push the down key to go to the sample size, that will change to 180, which is 80% of 225. We have to pick our appropriate alternative hypothesis. In this case, it's the third one. Right? We want to test whether the probability he makes a shot is greater than some number, in this case, greater than 75%. Here's the output. The main things of interest in the output are the test statistic, which is the 1.73, and the p-value, which is the 0.0416. And so here they are, step 2. Step 2 is construct our test statistic. As we saw, our calculator told us that that's 1.73. That means that the sample proportion, right, still has the same interpretation. The sample proportion is 1.73 standard deviations above the hypothesized proportion. Step 3, where's my p-value? Our p-value was 0.0416. That means that if AI really was just a 75% free throw shooter, that is, if he really was just an average free throw shooter, if the null hypothesis was true, then there's only a 4.16%, a very small percent chance that he would make 80% or more of 225 shots. Right? If he really is just average, it's unlikely that he would do as well as he actually did. And so what's more likely is that he is a better than 75% free throw shooter. Which is what we decide here. We compare our p-value to our alpha. In this case, it's smaller than our alpha. Whenever the p-value is less than alpha, we reject the null hypothesis. So, we would say at the 0.05 significance level, there is enough evidence to conclude that AI, that Allen Iverson, is a better than average free throw shooter. Huzzah! Next example. So, using data gathered over the last 20 years, it's determined that there is a 40% chance of rain for any given day in August. Now, it's thought that recently, right, as of this year, this number has actually changed for a variety of reasons, perhaps global warming. So to test this, we would have to what? We would have to pay attention last August, and let's say that we did, and we observed that of the 31 days in August, it rained in 7 of those days. So using this information, let's test the above claim. This idea of of global warming is somewhat politically charged, so let's use a perhaps slightly more rigorous rule of thumb than usual. Instead of the usual 0.05, let's use 0.01. Step 1, set up our hypotheses. So we are interested in whether or not, right, the probability it rains on any day is something other, has changed from 40%. Maybe gone up, maybe gone down. So our alternative hypothesis is that P is not equal to 0.40 versus the null hypothesis that P is equal to 0.40. We fill our information into the calculator. We know that it rains 7 days out of 31. Our hypothesized proportion, our P0 is 0.4. Our alternative hypothesis is not equal to. We fill all that information in, and here's our output. Right? The main things of interest are our test statistic, which is 1.98, sorry, negative 1.98, and our p-value, which is 0.0477. Now, it gives us our p-hat, which in this example is interesting, right, and good to know. So what was 7 out of 31? It turns out 7 out of 31 was about 22.5%. So 22.5% is certainly less than 40%, but is it so much less than that we think it's very strong, very convincing evidence, right, that the true proportion is something different than 40%? Is it far enough away? Well, that's what we need to explore. We already got this from our calculator. Our test statistic is negative 1.98. That means that the sample proportion is 1.98 standard deviations below the hypothesized proportion. The p-value is 0.0477. This means that if there really was a 40% chance of rain for any given day in August, it's fairly unlikely, as only a 4.77% chance of observing a sample proportion is far from 40% as the 22.5% was, right, or further away. Now we have to make our decision. We're comparing the p-value to alpha. Remember, for this problem we were told to use an alpha of 0.01. So 0.0477 is more than 0.01. Anytime our p-value is more than our significance level, we fail to reject the null hypothesis, right? So at the 0.01 significance level, there is not enough evidence to conclude that the probability it rains on any given day of August is different than 40%, right? Do you see why I always start these sentences by saying what the significance level we used is? It's important, right? Because if we had used the usual 0.05, do you see, we actually would have made a different decision. If we had used 0.05, now our p-value is less than 0.05, we would have rejected the null hypothesis. If you're making a decision or a conclusion, it's important to communicate to people what criteria you use to make that decision. Now, to be honest, to be truthful, in real-life literature, in real-life sort of graduate or academic level publications, the researchers usually do not just publish a conclusion. The researchers actually often will tell you the p-value of their study and leave it to you, the reader, the consumer, to sort of use your own personal alpha level in terms of deciding whether or not that p-value is, say, significant, right? All right, here we are. Example last. So last year, 65% of all Californians voted Democrat. It's thought that this proportion has since decreased. To test whether or not that's true, 144 voters are sampled, and 80 of them, sorry, not 80%, 80 of them say they plan on voting Democrat. Let's test the above claim with a slightly more relaxed alpha of 0.10. Now, before we go to the next slide, can you set up the alternative hypothesis? Good. It's going to be that P, right, the alternative hypothesis is that P, right, we thought it's gone down, so it's that P is less than 0.65, which of course is what's on this slide. So here it is, filling in the information, just the usual stuff. Hypothesized proportion is 0.65. 80 out of 144 people said that they planned on voting Democrat. Our alternative hypothesis is less than, right, P naught. Here's our output. The main things of interest are the test statistic, which is negative 2.38, and the p-value, which is 0.0087. We can see the sample proportion, p hat, is 0.5555, right? So about 55%, which again is less than 65%. So 55.5% of my sample say they're going to vote Democrat. Is that so far below 65 that it convinces me that it's now true that less than 65% of the population will vote Democrat? Well, to answer that, we need to look at the test statistic. The test statistic is negative 2.38. That means that the sample proportion is 2.38 standard deviations below the hypothesized proportion. Based off that test statistic, we can determine the p-value is 0.0087. Calculator did it for us. This means that if 65% of all Californians really were Democrat, or at least were going to vote Democrat, then there's only a 0.87%, less than a 1% chance that we would obtain a sample of 144 voters in which 55.5% of them or less were Democrat. This is a very small probability. It means that our sample is inconsistent with our hypothesis. In this example, our p-value is less than our alpha. Anytime our p-value is less than alpha, we reject our null hypothesis, and we conclude at the 0.10, at the 10% significance level, there is enough evidence to conclude that the proportion of Californians that are Democrat is less than 65%. And that does it. I'm pretty confident. We'll see when I tab down to the next slide. But I'm pretty confident that this is the end of it. So this wraps up Chapter 6, and it's been a pleasure being your narrator.